Greetings, fellow learners. In this video, we are going to look at the whats, the whys, and hows of pointwise convolution. There's a lot to unpack, so let's get to it. Starting with a definition. So a broad definition of this would be that it is a 1x1 convolution that enables us to control the depth of channels in a convolution network while being parameter efficient. And it does this by enabling cross-channel transformations. There's a lot of words in here to unpack, but hopefully as the video goes on, this will become more clear. So AlexNet was the state-of-the-art for object recognition back in 2012. Object recognition is given an image. The network is going to give some categorization for that image. Now let's expand this architecture and also add some pointwise convolutions. Let's now go through a convolution network architecture in detail, and then we'll also work through trying to add pointwise convolutions to this architecture to make it more parameter efficient, and we'll also show how we can control channel depth as well. So let's get started. This here is an input image of 32x32x3. We then perform a convolution with a 3x3x3 filter, and this is going to be slid over the entire input in order to get a 32x32 feature map. And we have 64 such filters, and hence the channel depth here becomes 64. This is going to capture details like edges in a specific orientation at a specific location within the image. We then pass it into a Relu activation to capture some nonlinearity, pass it into a max pooling. This will help summarize information from neighboring pixels together and effectively reduce the size of our tensor. We then perform another block of convolution, activation, and max pooling. And the idea here is to understand more higher level features. So instead of just edges, maybe here we're learning more about shapes and other textures or patterns. We then also follow this up with a sequence of convolution operations with some optional nonlinear activations applied at every case. And these are then piped into a max pooling. We then flatten these into an feed forward layer. We pass it all the way through a connection of these densely connected layers to get an output of a 10-dimensional vector of neurons. And we're assuming a 10-way classification, hence we have 10 neurons in the output. And from here we can get a categorization. So if you actually consider this network and you count the total number of parameters here, you'll get almost 7 million parameters. And the most egregious part of this is all of these parameters are concentrated right here in these sequence of feed-forward connected layers. But we also have the second biggest offender, which is the sequence of these convolutions. So each of these convolutions, you can see they have many filters. So these many filters, paired with the fact that these are 3x3 convolutions, really racks up the number of parameters in each case, almost 500,000 to even 1 million parameters. And this, you can see, if we're trying to make much larger networks, it substantially does add quite a few parameters. So why exactly do we have such large number of parameters here when we're trying to make transformations? Here you can see that in each of these cases, we're just transforming channel depth. So these are 8x8 feature maps, but we have so many channels from 192, it transforms to 384, to 256, and also 256 here. And the reason we have so many filters, well, is because the previous layers have so many filters. But why do the previous layers have so many filters? Well, if you go all the way to the beginning of this network over here, you can see that this first convolution is basically going to be a sum of products of this filter over some region of this image. And so the output over here is just going to be some linear combination of these weights along with the image. And it is for this reason that, a 32 cross 32 feature map over here is going to highlight or be activated by edges, something that's linear, a very low level feature. And it's specifically like edges and a specific orientation. In a previous video, we actually saw exactly that. Like, these feature maps are only going to highlight very specific edges of specific orientations. And some of them are also, you can see that they're kind of doing the same things. And so you can see that it's actually like a very simple feature that is detected. Now, in order to compensate for the fact that it's detecting that each of these 32 cross 32 feature maps is detecting a very simple feature, we use an over-complete set of them. We use so many, like 64 of them. And the idea is that, for a very complex image signal, at least like one of these 64 filters will be activated to a good degree, as it can detect, the edges of specific orientations, and hence pass that information down through the network. And now the problem here is that because, this is so deep already to begin with, it's already 64 dimensions, much more energy needs to be expended by these like future convolution layers in order to summarize and aggregate that information. And it does this because it needs to detect higher level features such as like textures or other shapes. And this is only exacerbated as we go deeper in the network, as these now need to detect higher level concepts like faces or eyes, for example. And so I hope that kind of illustrates the problem of like why we have so many of these filters, and why just simply like adding these 3 cross 3 convolutions really isn't a great solution, because it just racks up the number of parameters in the network, making training difficult. So to solve this problem, as well as this more egregious problem over here, we can use pointwise convolutions. So let's actually rewrite this entire AlexNet architecture, but making use of pointwise convolutions for parameter efficiency. So in this revised network, we have much of the same. We have like the input, we have the convolution layer with the same number of filters and the same filter size. We go into the activation and pooling to get nonlinearities and summarization of these layers. And then right now we have this new operation at this second convolution. So previously in the first version, we made use of 192 filters. And here I'm only making use of 128 filters for now, and you'll probably see why later. But essentially we make, the convolution operation of this 3 cross 3 cross 64 on this 16 cross 16 cross 64 tensor. And if you do a sliding window, you'll get 16 cross 16 as a feature map. We have 128 filters, and so the channel depth is 128. Now what we do is we perform a 1 cross 1 convolution. So essentially, we just take a 1 cross 1 cross 128 slice, that's like 128 1 cross 1 feature map section that highlight 128 activations for the same pixel space or receptive field. Now, on performing this, we have like a filter here, which is also 1 cross 1 cross 128. We basically take a sum of products, and what we'll end up with is just a single number that's right over here. And this is essentially information across all channels for like that same region within the input space. So for all those 128 feature maps, now all of that information has interacted with each other and has been summarized right here in this one floating value. And similarly, we move this one pixel at a time until it covers the entire image. So that would be like 16 cross 16 effectively. And we have 128 such filters, and so the depth is now 128. So what you can imagine now, the difference between this and this is that like this one has all of these individual 128 channels have now interacted with each other in different ways to create this new 128 cross 1 cross 1 channel depth. And so it's going to be much richer in features that are detected. We again perform now a 1 cross 1 convolution. This time now I want to expand the network. Now what this allows us to do is that we can control the depth of the channel of these tensors using a 1 cross 1 convolution by expanding it from like 128 to 192. And just doing this is now going to only incur a small cost of like 24,000 additional parameters. And remember, the reason we want to do this is for adequately summarizing and aggregating information across different channels. And this allows us to effectively do that while only incurring this cost. So that's nice. Now we can do a max pooling as we had done before. Again, 8 cross 8 cross 192 tensor. And now over here, what I'm also doing is instead of going from like a 192 directly to like a 384, which is kind of what we did in our AlexNet. Let me go back to AlexNet and just show you that. This conv3 went from like 192 over here to 384. But doing so, it incurred a cost of like adding 663,000 additional parameters. Very expensive. But we can kind of semi-avoid that by, instead just only, hiking it up to like just, let's say 256 filters. And so we get this output. And then we let the 1 cross 1 convolutions handle the other increases. So this is just adding more, mixing of these layers. This 1 cross 1 convolution is just going to, mix these up, make them all interact for richer features. And then we use this convolution, this little like 1 cross 1 pointwise convolution. It'll control again the depth of this channel by expanding it from 256 to 384 while incurring a small-ish parameter increase. So overall, you can see that the parameter increase is a little less than it was before, but you can see that as we've gone deeper, the actual like difference becomes more apparent, and the utility of these 1 cross 1 convolutions become more apparent. So we can do it again. For example, let's take this 1 cross 1 convolution. We take the output of 8 cross 8 cross 384. That's our new tensor. We apply some nonlinearity to it. Then we apply some summarization with max pooling. We get a 4 cross 4 cross 384 tensor. Great. Now what we can do is, let's look at our previous AlexNet architecture. We had like this layer, which incurred, again, because of this 384, it's pretty massive. So it incurs another almost million parameter increase, 84,000 parameter increase. But we can try to avoid that here by only making it like, again, I'm just using a 1 cross 1 convolution over here to reduce the number of channels from 384 to just 256. I'm using 1 cross 1s to control that channel depth. And now with this slightly reduced channel depth, I'm going to use the more powerful yet more expensive 3 cross 3 filters as convolution over here. And it incurs like a 589,000 additional parameters here. But this was overall a net decrease, right? It used to be like 884,000 parameters. Now it's just like 589,000 plus 98,000. So that's like 689,000, and maybe plus like another 65,000 since we're like adding more richness to each of these individual channels along the depth. And now what we're going to do is we wanted to get rid, in the original AlexNet, let's just go back. We have these like, we take this tensor, we're going to flatten it out. We get like 4,000 dimensions, and then we want to like pipe it to these feed forward sequence of like feed forward dense layers. And this incurs like well over like 4.5 million parameters. Now, the beauty of a 1 cross 1 convolution here is that we can now take, let's say, along this channel depth, we'd again perform a 1 cross 1 convolution using like 1 cross 1 cross 256 filters, and we reduce the channel depth from 256 just down to 10. So we basically take these 256 numbers over here. When you apply 1 cross 1 convolution, you just get a single number here that represents like interacted information, you only use 10 such filters to get 4 cross 4 cross 10. Thus, we effectively reduce the channel depth. And then what each of these 4 cross 4 activations are, well, for 10 object classification, each of these 4 cross 4 feature maps just represents the extent of activation for each of those objects. So for each 4 cross 4 tensor, we just take the average to get a single number. And we do that across each of the 10 channels to get a 1 cross 1 cross 10 tensor. And then we can flatten that out right over here in order to determine the final object classification. And so what's really cool about this is that we have the big ones that we saved a lot of parameters just by removing those feed-forward layers over here. And we were also able to save quite a few parameters along this way just by using these 1 cross 1 convolutions to expand or contract the number of channels in the network. And in doing so, the number of parameters now becomes 1.478 million instead of like the previous 6.97 million. Dramatic parameter decrease while still getting the power that we need. Now, to illustrate, these networks and exactly like how powerful they are in, their performance, I wrote the code right over here, which basically compares like 3 networks. First is the vanilla AlexNet architecture, which is exactly as I described in that first scenario. Then with all its like feed forward connection layers. And then I modified this Alex network in order to add just like that last layer, just like flattening it out and using that global average pooling that we discussed right over here. And then I also use this network in network architecture, which is again exactly as we described over here, along with like the global average pooling and pointwise convolution mechanism too. Now comparing them, we already saw this case 1, it's 6.9 million, that's what we saw previously. This third case is also what we saw, which is 1.48. And this middle case was like the same as the first case, but with no FC layers, and that's like 2.2 million. So we can see that already the number of parameters has reduced from the first case, from like removing the FC layers. That's a dramatic reduce right here. And we can also reduce parameters with just like trying to use these pointwise convolutions throughout the other parts of the network too. So that's nice. Now when you do some training and evaluation of all 3, you see that the first network, we've had an accuracy, or, training for the same parameters the same way. We just see an accuracy of like 78% for the first case. AlexNet without the FC layers, we have an 81%, so it actually improved despite the massive reduction in parameters. And then this last case we see it's 74%, which further reduction parameters have been made, but it's actually still quite comparable. So overall, the conclusions that we can draw from here is that during convolution, large number of filters appear in different layers. Thus, each additional convolution layer becomes expensive as it adds potentially millions of parameters to the network. With pointwise convolutions, we're able to control channel depth at any point in the network without adding too many learnable parameters to the network. And in the example above, we control the number of parameters in the network to drop by 30% compared to just AlexNet throughout the network with pointwise convolutions throughout the network, and even like 5x compared to the original AlexNet. And yet the training performance remained almost comparable, if not even better in some cases. So I hope the utility of pointwise convolutions is now more clear. Quiz time. Have you been paying attention? Let's quiz you to find out. So why do we use pointwise convolutions? A, to add nonlinearity to convolution filters. B, to summarize the effects of previous layers. C, to easily visualize the classification output activations of the network. Or D, to control the channel depth in deeper layers. I'll give you some time to answer this question. The correct answer is D. But can you tell me why? Comment your reasoning down in the comments below and let's have a discussion. And at this time, if you think I deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time, but before we go, let's generate a summary. So we started this video out with a broad definition of pointwise convolution. It is a 1x1 convolution that enables us to control the depth of channels in a convolution network while being parameter efficient. And it does this by enabling cross-channel transformations. And in order to see this in action, we took a look at the original, architecture without any pointwise convolutions. Then we took a look at an architecture that uses pointwise convolutions to demonstrate the reduction in parameters. And then we compared the architectures of the AlexNet with FC layers, the AlexNet with no FC layers but uses pointwise convolutions in the output instead, and then the AlexNet with only pointwise convolutions throughout the network, and saw that their performances were comparable despite the various differences in number of parameters. And we drafted those conclusions as well. And so that's all that we have for today. I hope everything here made sense. I'm going to put some resources to the code down in the description below, as well as the architecture diagrams too. As an added bonus for the architecture diagrams, I'm also going to show here how each of these pointwise convolutions is actually similar to just a feed-forward layer across these channels. So I hope that the visuals will make sense, as well as, some of the notes that I've written over here and also up here too make sense and also make that pretty clear. So that's all I have for today. Everything will be in the description below. Thank you all so much for watching, and I will see you in the next one. Bye-bye.